In this video, we're going to go over one of the problems from the example test that we didn't have time to go over in class. This is problem 10, where there is an infinitely long air core coaxial cable with a solid inner radius of A, I'm running out of space already, A, and an outer radius of B. And what they do is they apply a constant voltage and ask you to use Laplace's equation to find the electric field intensity. We didn't discuss that in our class because we don't have differential equations as a prerequisite. So instead, we assign a charge plus Q to the inner conductor and minus Q to the outer conductor and use that to find the electric field intensity. So, part A, electric field intensity. What is that? That is E. So how do we find E given this Q? It says air core, so we know that the material in between here just has epsilon naught and mu naught. And then what we need to do is figure out what the electric field intensity is between the two conductors. So, in order to do that, we apply Gauss's law. And if you remember, Gauss's law is that the closed surface integral of the electric flux density dot ds is equal to Q enclosed. Now, since D is epsilon E, we can also write it as epsilon E dot ds. And if we have the usual situation where epsilon is a scalar that doesn't vary with position, epsilon can come to the outside or we can divide through it. And that's how we get the multiple different forms of Gauss's law. In this case, in particular, we have epsilon equals epsilon naught. So we're going to do that. Our first step towards applying Gauss's law is to choose a Gaussian surface. Now, this is our cross section of our line. We have a plus Q charge assigned to the inner conductor, a minus Q charge assigned to the outer conductor. What should be our Gaussian surface? It's going to be a cylinder of radius r that's centered with the center conductor of this coaxial cable. I say cylinder because we're going to give it a height delta L. And when I guess implicitly we did that up here where we assigned these charges plus Q and minus Q, because if this is an infinitely long coaxial cable and we assign a charge to it, we divide that finite charge by infinite length, and there is actually no charge per unit length. So we're going to look at a length delta L of this coaxial cable and then use that to find the capacitance per unit length. Eventually. Right now we're just finding the electric field. So that's our Gaussian surface. If I just draw the Gaussian surface, it's a tiny cylinder. It has a top and bottom, and it also has sides. But by symmetry, because of the fact that this coaxial cable has a constant cross-section forever and ever, we can say that the electric field will only have a radial component. We're going to write that as E equals A hat R E sub R. So it only has a radial component. Then, looking again at our Gaussian surface, we can see that only the vertical sides, or the sides that are circular, are going to contribute to our Gaussian integral, because I'm coloring it in red. Because on the other sides, the top and bottom side, E dot ds is going to be 0. Well, on the circular side, E dot ds does not equal 0. See that? So, with that in mind, and we can also say that, again, because of symmetry, E sub r is only a function of r. It's not going to depend on z or on phi. So then, putting that into our Gaussian integral, we have epsilon naught times the closed surface integral on this surface that we've defined right here, E dot ds. Now ds is going to be r directed, and so is E. So that's going to be epsilon naught integral over the closed surface of E sub r ds. Now this is ds, not the vector, so we're just multiplying here, which is going to be equal to the q enclosed, which is the positive charge. What is ds in our case? ds, we have to do our integral all the way around in phi, so we're going to get an r d phi from going in that direction, and then we're also going to get a dz from going up and down. So that's going to be r d phi dz. Then we have epsilon naught integral from z equals 0 to delta L, integral from phi equals 0 to 2 pi, E sub r, which is only a function of r, remember, times r d phi dz. Now, since E sub r is a function of r, and r is obviously also a function of r, neither of them depends on varying phi or varying z. So when we do this integral, we end up with epsilon naught delta L 2 pi E sub r times r is equal to the enclosed charge. Ran out of space a little bit there. But that is going to mean that E sub r, the magnitude of our r-directed electric field intensity, is q over 2 pi delta L r epsilon naught. And remember, we were asked for the actual electric field intensity, so that is E, the vector, which is going to be E is a hat r times q over 2 pi delta L r epsilon naught. So that's part A of problem 10. They, since they started you off with a voltage, asked you to find the charge density on the inner conductor next. Instead, we're going to do it the other way around. So part B is going to be find the voltage. For that, we start with voltage equals minus the integral of E dot dl from conductor 1 to conductor 2. And we're going to say that conductor 1 is outer and conductor 2 is inner. So it's going to be minus q over 2 pi delta L epsilon naught integral from B to A of 1 over r, and dl is going to be dr. I kind of skipped the step where we do the dot product between E and DL there, but we're taking a radial path, so E dot DL is just going to be the magnitude of E. Excuse me, sorry about that. So, in my next step, I just have to evaluate this integral. So I keep all the constants on the front exactly the way they are, minus q over 2 pi delta L epsilon naught integral from B to A of, actually I'm evaluating this. So the integral of 1 over r is ln of r. So we're going to have ln of A minus ln of B. And because of our natural log identities, first of all, we're going to cancel out this minus sign and swap the order of these things. So that's going to be minus ln of A plus ln of B. Then we're going to write all the constants down again, q over 2 pi delta L epsilon naught. And then combine our two natural logs into one, because when you subtract natural logs, it looks like division in the argument. So that's ln of B over A. So then, in part C, we are asked to find the capacitance per unit length. In order to do that, first of all, we will take the definition of capacitance. Capacitance is Q over V, charge divided by voltage. Per unit length capacitance, C per unit length, is equal to Q over delta L divided by V. Because we have to do capacitance per unit length, so it's going to be a charge per unit length also. Applying that, our charge per unit length is just Q over delta L, and our voltage we found in part B. So that voltage is Q over 2 pi delta L epsilon naught times ln of B over A. And if I work all this stuff out, my delta L's cancel, my Q's cancel, and I end up with 2 pi epsilon naught ln of B over A. Nope. The ln goes on the bottom still. Sorry about that. Divided by ln of B over A. Yep. And that's all there is to it. So that is our capacitance per unit length. And then in part D, they say, given the field intensity determined in A, write an expression for the electric field intensity propagating down the coaxial line in the positive z direction if the applied voltage varies harmonically. For that one, you have to go back to the fact. Well, let's skip that one. There's not going to be that one.